We are recording now this lecture. I think you agree with that, Professor Lehnert. Perfect. So welcome everybody to the second quantum seminar in this semester. At the beginning, let me briefly introduce to you our speaker for today. Professor Lehnert, he got his PhD in physics in 1999. Actually, the time when I enrolled in the university in Munich. He got it from University of California at Santa Barbara in California. His dissertation was about non-equilibrium dynamics in mesoscopic semiconductor superconductor junctions under the supervision of Professor James Allen. And after he got his PhD, he was working as a postdoctoral associate and then as an associate researcher scientist at the Yale Applied Physics Department in New Haven, Connecticut. And then from 2003, he was a physicist at the National Institute of Standard and Technology, NIST, and the JILA fellow. And then he got the assistant professor of physics, adjunct professor in 2007. And then in 2 years later, associate professor of physics. And then in 2014, a professor of physics at JILA at the University of Colorado, Boulder. And he got many awards and honors. I don't want to listen all of them, but I think what I now remember is the fellow of the American Physical Society in 2013. Yeah, Professor Lehnert, we are happy to have you here with us today. We are looking forward to listen to your talk about quantum enhanced sensing and fundamental physics experiments. Please.
Thank you very much. It's a great pleasure to be here. Good afternoon to those of you in Europe. Good morning to anyone joining from North America, also South America. Today, I'm going to tell you about quantum enhanced sensing in fundamental physics. That's title is a little more general. The talk will be predominantly about the search for a particular kind of ultralight dark matter known as the Axion. And the experimental aspects of that I do in a collaboration. We call ourselves Haystack, and it's a collaboration of these 5 groups at these 4 universities. And the main experimental result from that recently was the PhD work of Kelly Bacchus at Yale and my student Dan Palkin here in JILA. And then in my group, we have a team of people who think about quantum enhanced sensing in dark matter searches. Okay, so in outline, what I'm going to tell you about today, by advance my slide. There we go. I'm going to tell you about that search for ultralight dark matter, a particular class of dark matter problems. It's really a problem that you want to analyze and think about using the framework of something called quantum metrology. It's very natural from that perspective. I'll give you just a very brief introduction to thinking that way. And I'll show you that a class of these ultralight dark matter models known as the Axion, that kind of a search really benefits from this emerging quantum circuit technology associated with superconducting quantum computers. The main experimental result will be that quantum squeezing, a particular kind of quantum enhanced measurement strategy, that's accelerating the Axion search today. This is happening now. We can search for Axions more rapidly than if we allowed quantum mechanical fluctuations to limit us. So we can, it's possible with reasonable developments that we could substantially accelerate an Axion search, that we may be able to go much faster. All right, so to get us going, I will start with a slide about dark matter. I'm the wrong kind of physicist to tell you what dark matter is. I don't know that much about it. Fortunately, no one knows that much about it. Basically, what we think we know is that of the matter in the universe, the stuff that gravitates, 85% of it seems to be made of stuff that we don't know what it is. It's detected only through inference in astrophysical observations, cosmic microwave background, essentially through the fact that it influences other things that we can see gravitationally. In our laboratories, there's no signal yet that we can detect or assign to the presence or absence of dark matter. We know that, it's cold in the sense that it has to be kind of gravitationally bound to us and we to it, and that means that its velocity distribution is very much non-relativistic. And locally, meaning kind of in our local galaxy, it has some mean density around half a giga-electron volt per cubic centimeter. And that's about it. Now, for lots of good reasons, it's thought that the dark matter has a fundamental particle origin. It's essentially made of some fundamental particle that isn't yet part of the standard model. It hasn't been seen in some accelerator experiment, but there are lots of good reasons to think that that's the origin of this. It's some very weakly interacting fundamental particle. Lots of different ideas about what those fundamental particles might be. If the rest mass of those fundamental particles are less than about 1 electron volt, that puts you into this world of so-called ultralight dark matter, sometimes called wave-like dark matter. And the upshot is, in a world that knows a bit about quantum gases, you'll appreciate this, given the density, the mass density of the particles and their mass, you know their number density, you have some notion of their velocity distribution. Essentially, lighter than about an electron volt, the dark matter would have to be in quantum degenerate Bose gas. As such, you should think about the laboratory phenomenon. The thing that you're looking for is really more of a wave-like than particle-like phenomenon. Rather than imagining that some massive particle very rarely is going to scatter off a heavy nucleus inside of some jacuzzi filled with some xenon or argon and make a little flash very rarely. Rather, you're looking for some oscillatory phenomenon, a tone, very feeble, because otherwise we would have already seen it, but it's always there, it's persistent, and it's at some unknown frequency. And a kind of search for this kind of dark matter is a search through frequency space. So many of the experiments in this kind of ultralight dark matter search, they have a kind of an appearance that's common to many of the apparatus. They are some kind of laboratory high Q harmonic oscillator, microwave cavity, an LC circuit, an ensemble of electron or nuclear spins, something that you describe as a sort of single degree of freedom, more or less a harmonic oscillator. And there are these kind of high energy physics collaboration names that go with some of the prominent experiments in this field. That high Q oscillator, it's usually tunable so that you can hunt through frequency space. And it has some putative coupling to the dark matter field. The nature of the dark matter is that this coupling has to be weak. It has to be very, very feeble. Our only hope of detecting the dark matter is, in some sense, because it's such a highly occupied field. This is a very, very highly occupied field, very weakly coupled to a high Q oscillator in our lab. And the hierarchy of couplings is such that no matter how hard we try, this high Q oscillator, no matter how hard we work to make it high Q, it's always going to be coupled to its environment. Its primary cause or origin of its quantum decoherence is going to come not from the coupling to the dark matter, but to the coupling to stuff in the lab that we don't control. So once we say that, we can think of the dark matter coupling as exerting a classical force on our harmonic oscillator. In the right variables, it's very easy to think about the dark matter search as a kind of hypothesis testing. You're trying to distinguish whether your laboratory harmonic oscillator evolves under this null hypothesis, or whether it's being the coordinates that describe the state of the harmonic oscillator are being pushed, are being shoved around in phase space by some classical force. And in particular, if we say it's a classical force, what that really means is that we should just think about the coordinates of phase space as having some interaction, the Hamiltonian, which has some unknown coefficients in front of it. These are classical numbers that sit in front of the quantum quadrature phase space variables of our harmonic oscillator. It is our job, it is our goal to estimate these parameters that appear in the Hamiltonian. This is a Hamiltonian parameter estimation problem. And in that sense, it's really amenable to analysis as using the framework of quantum metrology. Basically, we can imagine an experiment. Our harmonic oscillator will begin in some state. I've written it here as some pure states, could be mixed. We prepare it in any state we desire, at least in principle, we can imagine doing that. Allow it to evolve under the Hamiltonian with its unknown parameters, and measure any thing we like, any valid physical observable of that harmonic oscillator. We measure that quantity. The laws of quantum mechanics tell us how to turn that into a probability distribution of outcomes where that distribution depends on these unknown parameters. And then you have a classical statistical inference problem. What is the likelihood that you measured a particular value in your experiment given the values of these parameters? The framework of quantum metrology says, let's think about what would be the best possible initial state to prepare the system in, and what quantity would we want to measure. And the choice of those things represent a strategy, a kind of quantum metrology strategy. In this world, the phrase quantum limit gets used a lot. I think it's maybe overused or used to mean different things in an awkward way. I think when I'll say quantum limit, what that really means is a particular strategy. It means that we're going to prepare the harmonic oscillator in its quantum ground state, allow it to evolve, and measure one of these quadrature amplitudes noiselessly. We can represent what that looks like. We can draw a picture of that in a phase-space distribution, plotting the quadratures in some orthogonal phase-space picture. The ground state, because these quadrature amplitudes don't commute, because they're canonically conjugate, the phase-space distribution will be some blob of quantum mechanical uncertainty centered on the origin. And that's in the absence of dark matter. If we wait for some period of time and there is a coupling to a dark matter field, that phase-space distribution is going to be displaced from the origin. Pretty clearly, the fact that there's this blob of quantum mechanical uncertainty, that our ground state is not an eigenstate of either of these variables x or y, means that that's going to influence or pollute our inference of this classical force. We're going to have to wait longer to decide whether or not such a classical force is present than we would, in the absence of these quantum fluctuations. And that fact that we can only search for this dark matter with a certain sensitivity, given a certain amount of time we're willing to wait, that's a limit, and that sort of defines the quantum limit in this case. We might be happier if we called it the coherent state limit, but this phrase is pretty standard. Okay, can we do better? Well, sure. So here's a different quantum metrology strategy. You could prepare the harmonic oscillator close to an eigenstate of the variable that you will eventually measure. In this case, a state which is squeezed in the X quadrature. Really talking about a completely unitary deterministic transformation of the quantum ground state by squishing the phase-space coordinates in one axis and stretching them in the orthogonal axis. That makes a squeezed state. The more squeezed it is, the closer you come to an eigenstate of the this X observable. You let it evolve for some period of time. If there's a dark matter field and you measure X, clearly you can more rapidly infer the presence or absence of this classical force, at least the part that would displace you in the X coordinate, in the X quadrature. Now, I think this story sometimes invites the idea that the erroneous idea that we are kind of circumventing or beating the quantum limit by the choice of giving up knowledge of one quadrature of this dark matter field, the Y quadrature, at the enhanced sensitivity to the X quadrature. What I'd like to emphasize before I go on is that you absolutely can measure both quadratures, both components of this displacement, without the influence of the quantum noise, at least in principle. Just to kind of describe to you how that might work, you would start with two harmonic oscillators, one being the dark matter coupled system, one being some ancillary harmonic oscillator. They would both start in their quantum ground state. Then you would prepare that two harmonic oscillator system in a state which is a so-called two-mode squeeze state or entangled state. Basically, the final state of the two cavities would be an amplified linear combination of the initial state. And it, of course, looks like there's more noise after this unitary transformation. There isn't more noise, that there are strong correlations between these two harmonic oscillator modes. That's what we mean by saying that they're entangled. If you let that state evolve, if there is dark matter coupling, you would displace the dark matter coupled cavity in phase space. And then all you would need to do is undo this squeezing operation, this unitary process. The correlations that are present, they were created in the first place by this entangling operation. Now you just undo them. That returns the fluctuations back to their disentangled quantum origin. But the uncorrelated piece, which was the displacement of the phase-space distribution from the origin, that gets amplified in both cavities. And then you're at liberty to measure the X quadrature of one harmonic oscillator, the Y quadrature of the other. Those commute, so there's no noise associated with measuring both of them. And to the degree that you could make the gain, the amplification here, arbitrarily large, you could have arbitrarily good sensitivity to this initial displacement. All right. So this is like these ideas, they have been around for a while now. This quantum limit, though, it's hard to beat in a search for fundamental fields. Like I got introduced to these ideas when I was reading about the efforts to detect gravitational waves. There's a paper now published I used to say 40 years ago, but it's even longer now. It's essentially 41 years ago. You know, and you can see that it was published in a Review of Modern Physics, so it's really been around for a while. These ideas, there aren't that many instances of these ideas being deployed or used in the search for fundamental phenomena like gravitational waves, which is what this paper is really about, or the search for dark matter or other things. In some sense, that's, you know, for a few different reasons. If you're coupling to some fundamental phenomena that's present but very weak, usually you need a big thing like this 1-ton Weber bar used in early searches for gravitational waves, you know, compared to some 5-micron diameter aluminum drum would be a thing that we would study in our lab. You know, this thing couples to gravitational waves in a meaningful way. This thing you have quantum control over. Their scales are just wildly different. And it also requires like a real technical perfection. If you have lots of technical noise associated with the measurement, the preparation of states, you needn't bother with lots of these quantum enhanced strategies. So there aren't that many places where you're able to really have quantum control and measurement over relatively large systems that would meaningfully couple to some fundamental phenomenon. So an exception to that fact, like a counterexample to that, is in the search for Axion dark matter. So I'll tell you that story. So maybe I'll say what few things I really know about the Axion. It's a hypothetical particle. It was hypothesized not as an origin for dark matter, but really to explain a strange experimental fact. We know that the charge parity symmetry of the charge parity symmetry is not a good symmetry of nature. It is, however, an extraordinarily good symmetry of the strong sector of quantum chromodynamics. That's known experimentally, for example, from the fact that the neutron has as yet an immeasurably small electrical dipole moment. It is, in the language of these kind of searches for the neutron dipole moment, an incredibly round particle. So you can account for that fact by positing the existence of some other scalar field that couples to gluons in the right way. And then in our low energy state of the universe, the CP violating terms, which would naturally appear in the strong sector, get driven to zero in a dynamical process. The low energy excitations of that field are what we call axions. From astrophysical reasons, the mass of the axion, it's constrained experimentally to be less than about 2 millielectron volts. There's really no bound on how light it can be until you get to things like it's somehow bigger than a galaxy. Its Compton wavelength would be bigger than a galaxy. So, but if you think of it as having like the process that drove the CP violating terms to zero is happening after the hypothetical era of inflation, there is a sort of weaker bound, you can say, given that hypothesis, that you would just have these 3 orders of magnitude in mass, and therefore these 3 orders of magnitude in Compton frequency to search over.
Konrad, sorry for the interruption, but the question is, how do you deal with interruptions? I mean, we forgot sort of to
discuss this topic?
No, just like in general. Shall we just interrupt you with questions? Do you want to
why not?
Questions at the end? Or because I saw that Dima was getting...
I saw Dima's face pop up, and he was probably
I was getting nervous of you're excluding all our work for the last 5 years, but which is exactly in that very low mass region. But you said it. I think that in principle there is no lower limit except 10 to minus 22. But some theorists prefer this range. But as you said in the beginning, we don't know anything about dark matter. So I think
Dima, to be clear, the asterisk here. So the way I think about this very specifically is that I like, in this problem, it's useful to assign prior probability to what you think is true. And the way I would think about it is, in order to narrow the range of frequencies over which we would imagine searching, we can declare that we're going to limit the hypothetical, range of things we're looking for. We can then say, well, what probability do you want to assign to this being a post-inflationary scenario? It's not 0. That's good. It's certainly not 1. It's some number say it's a 20% chance. Who cares? You can kind of make a Drake equation for this thing, and then you have a finite region of parameter space to think about. And you can tell me, like, I can tell you, how much did my experiment teach you by not finding something? If it's an infinite parameter space, then of course any finite exclusion of parameters, of course, is somehow actually empty.
You mean the Drake equations about the probability of aliens?
Yeah, so this is a Drake equation about the probability of axions.
Well, if I would motivate a cavity search, then I would probably also start somewhere in the 500 megahertz range.
Well, so the answer is I have absolutely. If you want to find a theorist who will tell you not to look below or above a certain frequency, I'm sure you can find such a theorist. Ultimately, as experimentalists, it's up to us to make choices about which parts of this hypothetical space to search in. I like to search in the space that I'm working in because it uses microwave superconducting circuit technology. Okay, I'll move on. In that low energy limit, the Axion field, it couples to electromagnetism. It adds a term to the QCD Lagrangian that would be the Axion field couples to E dot B, this sort of pseudo-scalar combination of electric and magnetic fields. In some kind of fanciful Feynman-like diagram, you can imagine the Axion splitting into two photons. To a kind of quantum engineer like myself, I just look at this expression and say, oh, what I want to do is linearize this three-field interaction term around a big static field, like make the biggest DC magnetic field I can. And then there's a linear interaction between the axion and electromagnetism, such that axions can decay into photons. And if they are dark matter axions, more or less at rest with respect to us, that would make a microwave photon. And that becomes interesting to me because measuring microwave photons is a thing I think I know how to do. And there's lots of superconducting circuit technology that now accesses quantum states of microwave fields. You can benefit from the existence of these parametric amplifiers. They do things like measure single quadratures noiselessly, prepare squeeze states. You can count photons using superconducting qubits. You can route fields around losslessly using superconducting microwave switches. And it's useful to now think about this problem because the other thing to do when you have these kind of quantum metrology problems is just, invest more resources, spend more money, wait longer. But the signal increase we'll see is prohibitively expensive in this axion search world. So what does an experiment look like? Well, our harmonic oscillator, it's a microwave cavity, something about 1 liter in volume, tunable mechanically by some rod that rolls around inside of that microwave cavity, changing the resonant mode. And it has a frequency of a few gigahertz. You stick that cavity in the biggest magnetic field that you can get your hands on, and then you try to measure 1 quadrature of the harmonic of the dark matter sensitive mode in that cavity. And in particular, the way you do that is by punching a hole in the cavity, letting some of the microwave field leak out, and directing it to a microwave measurement apparatus. In that case, it's one of these Josephson parametric amplifiers that sort of developed in our lab. And they do a very nice job of measuring 1 quadrature noiselessly. And that cavity is tunable so that you can hunt through frequency space. A little more in detail, the output of the amplifier is some a signal as a function of time. You can Fourier transform that, find the power spectral density in that noisy signal. You're looking for a peak in the noise, which pokes up above the background by about a part per thousand, where the background is now the quantum fluctuations, and the peak sticks up about a part per thousand above the essentially the 0 point or vacuum fluctuations of that microwave cavity mode. You're looking at to estimate the variance of a random process. If you're trying to estimate the precision to a part in 1,000, you need 1,000,000 such realizations. That means you wait for a while to average the noise, not finding an axion in your band of sensitivity, you tune the cavity and you do it again. So in current experimental constraints, the axion cavity is sensitive over a range of frequency, which we'll discuss in a moment, which is about 100 times wider in frequency than expected line width of one of these little peaks in the noise. So you have something like 100 independent little frequency bins that you're searching over. And it's pretty clear that the game then is to make the bandwidth bigger, to search over a wider frequency range without hurting the sensitivity, without making the signal any smaller. And if you can figure out how to do that, then you're doing better. So I'd like to, kind of express the quantum limit here as a kind of back action caused problem.
Konrad?
Yes, go ahead, Bill.
So I missed, how did delta omega axion come out?
What sets the natural line width of the axion?
Right.
So
what does?
This is basically the virial velocity in our frame on the Earth, or the distribution implied by the virial velocity in our frame on Earth. In order to be gravitationally bound to us, the Maxwellian-like distribution of stuff, including dark matter, should have kind of a peak at about 1 part per thousand the speed of light. And that means it's going to have an energy dispersion of about 1 part per million. If you imagine the rest mass of the particle giving you the sort of center frequency and the distribution around it being the distribution of velocities.
Okay,
does my answer make sense?
Well, is that consistent with it being Bose condensed?
Oh yes, exactly. That's precisely that Maxwellian distribution is in fact consistent with it being Bose condensed.
Well, I'm just trying to reconcile the idea of a Maxwellian distribution with a Bose distribution that is cold enough for it to be condensed. It seems like, the normal thing is if it's well below the condensation temperature, then the Maxwellian part or Bose part or whatever, thermal Bose part, is a pretty small fraction of the total distribution.
I suppose that's right, but now imagine that the phase of this Bose condensed distribution you don't know, and you're sampling different parts of it, and there's no particular reason why it should have a particular phase locally relative to some clock in your lab, and you're sampling lots of values over the time that you integrate. That ends up basically looking like this Maxwellian distribution.
Is it maybe? I'm also a bit struggling with that. We are thinking about this virialized velocity distribution currently a lot, and I always just nod and acknowledge that people consider it both condensed, but is maybe what they mean when they say that more like that the mode occupation number is high, but in all the individual modes. Right. It's not that there is like a ground state that is going to be populated. Right. It's not like you have something, and even though there is actually the gravitational potential in our galaxy, where you could think of maybe there is a ground state of this Bose gas, and then you would have, however, I believe, a different manifestation of dark matter.
I suppose. Okay, so fine. This is of course correct. Maybe a way to say it is the following. if you would imagine that Bill, this isn't going to satisfy you, but at least it's going to justify. Imagine this following. Say for sake of argument that it is Bose condensed and we just don't know the velocity with which we are moving through this stuff. And we're going to be very conservative, and we're going to say, well, it's going to be drawn from some, we expect a delta function that's going to be drawn from some distribution. How wide should we make the little bin in frequency over which we look?
Well, you're right that it's not. In fact, just as you said that this isn't going to satisfy you, I was writing in my notebook. He gives an argument that I don't find satisfying.
As far as I know, there are a community of people out there who think about exactly, what the spectral or temporal distribution would look like, and they're really doing simulations of like blobs of dark matter just treated like some classical gravitational fluid. And there are various things that look like not particularly Maxwellian in that. They would have a temporal and spectral component to them in some sense, meaning that if you knew just how to apply the right temporal filter to your data at the right moment in time, you would pick out some very narrow spectral distribution. I would say that this kind of Maxwellian story is one of being a little bit conservative, of sort of, if you were to, you can play a game, which is to say you can claim greater experimental reach by making assumptions about what this distribution would look like and claiming to hunt for it in your data. But in a way, that's sort of moving the goalpost without making your experiment better.
So what is this number?
So which number? The fractional...
delta omega axion.
Yeah, so it's a part per million of whatever you think the axion frequency is.
Okay.
That's basically a part in 10. So if the max, if we think of the peak of the Maxwellian distribution associated with the virial velocity is about a part per thousand the speed of light, then that energy dispersion is a part per million.
Okay. Okay.
Okay. All right, time to get back on track. Good, where was I? Yes, so I'm going to think about this as a kind of back action influence of the measurement. So we have our cavity, it has X and Y quadratures. We'd like to estimate the X quadrature. The way we're going to do that is by punching a hole in the cavity, letting the field in the cavity leak out and reach an apparatus that we say measures the X quadrature, or at least from which we can make an inference. The rate at which we're getting new information about the state of the cavity is controlled by how strongly we couple, essentially by how deep we stick coaxial cable into our cavity. And it's quite literally that. Associated with that measurement is some interruption of the Hamiltonian evolution of the cavity, inevitably. In a kind of open quantum systems picture, you can draw a picture of what causes that interruption of the Hamiltonian evolution. It's essentially the Johnson-Nyquist noise of some 50 ohm resistor in the experiment that sources vacuum fluctuations directed down the cable. And those interrupt the Hamiltonian evolution of the cavity. But we can assign a kind of physical origin to that measurement back action. And you can ask, well, what is the optimal measurement rate? How fast should we measure? To answer that question, it's useful to think about the intrinsic decoherence or loss in the system. The cavity will be lossy because it's made of copper and sitting in a big magnetic field. That loss and associated decoherence is not 0. And we would like to compare these two rates. Essentially, maybe to complete the picture, we can think of the Axion signal as coupling in also through some sort of fictitious coaxial cable, but this one has microwave generator hiding behind it, and it's incredibly weakly coupled compared to the other two rates in the problem. And so at least if this Axion signal we were lucky enough to have it beyond resonance with our cavity, what we could do is we could say, well, let us choose our measurement rate such that, well, it shouldn't be much smaller than the intrinsic decoherence rate, because then we could be measuring faster, getting more information at no penalty compared to the intrinsic decoherence rate that's already present. But then, of course, not much faster, because then our measurement itself is interrupting the Hamiltonian evolution of the cavity. The Axion field could be building up coherently inside the cavity for a longer period of time. So the optimum is really just to balance those two rates, to make the measurement rate equal to this intrinsic decoherence rate. In the language of microwave engineering, this is also critical coupling. This means that the incident microwave fields in this cavity right on resonance just get absorbed. And that tells us that the bandwidth, this kind of bandwidth over which the cavity is sensitive, is just twice the intrinsic loss rate. So that's a regime we reached about 4 years ago in this Axion search. And you plot in this world a kind of exclusion plot where the Axion coupling is plotted on the y-axis. On the x-axis is the unknown mass of the Axion, or expressed as a frequency on the top axis here. And your exclusion plot is basically a little region where you promise that at this sensitivity with some confidence, you say there is no Axion. One of the nice things about the Axion is that the model, the QCD, is really a band. It's kind of, the coupling doesn't go to arbitrarily small values. There's some range. And then there are these fiducial values named for the theorists who wrote the papers that tell you kind of how close you are to some fiducial value. If you wanted to get to the more pessimistic of these two values, using the parameters of the haystack apparatus, that would, at this more pessimistic coupling, searching over the 1 to 10 gigahertz region, just the 1 decade of frequency over this 3 decades that we'd imagine we'd want to search for, that would take something like 20,000 years. For those of you who are wondering what's going on, my toddler has awoken and she is chatting away the way that she likes to do. So I'll just try to to talk over her. Where was I? Yes, 20,000 years. You could spend more money, right? You could just buy bigger magnets and wait a lot less time, but it's substantial cost. And so there's really, I think, a strong need to do quantum enhanced sensing in this problem. That's what you need to do. So how do you do better? Well, in this quantum squeezing picture adapted to this back action idea, it's useful to understand that the Johnson-Nyquist noise sourced by this resistor that I'm drawing, that's a real physical resistor. It's actually something that we purchased for $80 from a microwave supply house. It's a 50 ohm termination. And it's sourcing vacuum fluctuations. We could squeeze those. And now the fluctuations that are going to drive the X quadrature of our cavity are suppressed. And as a consequence, we could measure more rapidly. We could increase the measurement rate even above this intrinsic decoherence rate, suffering no penalty, or not a substantial penalty, in the evolution of the X quadrature. The Y quadrature for sure will be perturbed more, but we're not measuring it. And then enjoy an increased bandwidth and therefore search faster. If you were to plot what this looks like, the sensitivity in the case that we would operate in the critically coupled situation without squeezing as a function of the Axion detuning from cavity resonance. Now, that's the sort of roll-off that you would expect associated with the cavity's line width. If you were to open up the bandwidth of the cavity, measure more strongly, measure more rapidly, and only modestly squeeze, just sort of suppressing the variance in the squeeze quadrature only by a factor of 3, but the bandwidth by a factor of 10, that would be a big win. And in particular, you can plot this sort of variance reduction on the y-axis here, the amount that you increase the measurement rate above this optimum value for the critically coupled case, and then plot the amount that you get to go faster than the scan rate in this color plot. And it looks fantastic. You could do hundreds of times faster. That notion confronts the fact that some of the squeeze state that you're generating in one location is going to get absorbed on its way to being measured. And that absorption, that does what it does to any squeeze state. It diminishes the squeezing in the squeezed quadrature. As a consequence, your scan rate enhancement is quite substantially reduced for only a rather modest amount of absorption on the way. Nevertheless, that factor of 2 is still worth chasing. So how do we measure and how do we squeeze? So the way that we do this kind of low noise single quadrature measurement, basically we build a parametric amplifier. It's really just an inductor, capacitor, resonant circuit, where the inductor itself is using the properties of Josephson junctions, something which can be tuned. You can vary the inductance, and you can vary it in particular at twice the natural frequency of this LC circuit. That's a very simple way to make a parametric amplifier. Microwave fields that enter or reflect off this LC circuit through this little coupling capacitor, they are reflected and amplified. That gives you narrow band gain, and you can then tune that narrow band gain around in frequency by not just adjusting the oscillatory flux, but the static flux that penetrates these little Josephson junction loops called squids. So that's what this little triangle is meant to show you, is basically an incoming microwave field that's reflected and amplified. If we build our world thinking about the frequencies with respect to some pump that we're using to pump the parametric amplifier, and that defines the frame in which these phase-space quadratures are rotating, we can think of the vacuum fluctuations and the coherent displacement of an incoming signal just being stretched, that is amplified in the X quadrature and squeezed in the Y quadrature. And the fact that you're really doing a phase space volume preserving transformation really means that these amplifiers in principle have no added noise. You just measure one quadrature noiselessly, the amplified quadrature. Of course, you could rotate the phase of your pump field by 90 degrees, and then you could squeeze a quadrature in the same object. You can strap one of these objects in series with the second one. Think of the first parametric amplifier as preparing a squeeze state. The second one is analyzing or measuring a particular quadrature of that squeeze state and rotating the relative phase of the two pump fields such that you squeeze in one axis and measure in another. As a function of that phase, you can plot the variance of the measurement of your X quadrature. Here's a histogram of all of the outcomes as you vary that phase in the color scale, and then the variance extracted from that histogram as this black line, where the vacuum fluctuations would be this green line, and you can go about 4.5 dB below vacuum. And that really corresponds to a loss of about 1.6 dB between the two parametric amplifiers. That's why this doesn't go down further. You can test the squeeze state receiver, like this concept of using a squeezer and an amplifier in a kind of demonstration experiment where you really want to show that you get the quantum enhancement that you claim. So the 3 ports I drew previously coupling to some Axion cavity, you can make a microwave cavity with 3 physical ports. one of which is intentionally there to model the loss of an Axion cavity, one of which is very weakly coupled, to which you connect a microwave generator that creates a kind of fake Axion, and then one which is the measurement port. You can vary how strongly coupled this port is to your microwave cavity, and look at whether or not you can recover this microwave tone more rapidly because you squeeze. So for an off resonance microwave tone, away from cavity resonance, you can see that the signal to noise with which you would see the tone in the case that you don't squeeze, and then in the case that you do squeeze, and you get that full 4.5 dB enhancement. And then you can do this as a function of the tones detuning from the cavity's resonance. In the case that you don't squeeze and choose to critically couple, it gives you your maximum on resonance sensitivity and some sensitivity bandwidth. You can then overcouple but not squeeze, and then overcouple and squeeze. And the signal to noise ratio is clearly improved when you squeeze, and a slight reduction in right on resonance sensitivity is more than made up for by the increase in bandwidth, allowing you to double your scan rate.
Yeah, excuse me. When you
Go ahead.
say the X quadrature, is that the X quadrature in the rotating frame?
Yes, that's right. So the pumps themselves define a rotating frame, and that's the X quadrature with respect to that rotating frame.
Thanks.
So we took that apparatus that we demonstrated in our lab. We went to Yale and worked there to install the system in a new dilution refrigerator, and ran the experiment. And it's being operated today. We wrapped up, this is, I guess, the picture of the kind of some members of the collaboration installing that system at Yale. That happened, I guess, back pre-pandemic. You can see no one has masks on. And we've completed that first data run. So we, compared to what we did at the quantum limit, we've now scanned over this little range in frequency, taking about 100 fewer days to scan this range than we would have if we'd operated at the quantum limit. And that's this recent publication. So is it doubling of the scan rate meaningful? Well, compared to the numbers I told you earlier, it would save you 10,000 years or $600 million. So I think, that factor of 2 is something. I think the other way to say it, though, is that given that there's no longer diminishing returns to improving the technical aspects of the experiment, to reducing loss, to making things work better, now there's a reason, a motivation to work on those technical things to get bigger improvements. So I'll mention a few things that we're thinking about in the last part of this talk to try to squeeze out some additional performance. So the real bad actor, why did we have 1.6 dB or so of loss between the generation of the squeeze state over here and its analysis over here? That really was predominantly associated with the non-reciprocal element, the circulator, that sits directing microwave fields down towards the cavity and then directing the reflected ones towards the measurement here. That's a commercial object. You buy it for money. It is made of non-superconducting materials. It's a little bit absorptive. That's reality. In addition, even if it were perfect, we are not perfect at directing our microwave fields without reflections. And if there are any reflections in this signal path, those reflections are directed back to the circulator, which does exactly what we ask it to do, which is throw away reflected fields. And so the combination of those two things, that's what gives you that 1.6 dB of loss. So our concept for doing better a little bit motivated by this story I told you at the very beginning about having two entangled cavities, is to pursue a better approach to back action evading measurements, is to have two cavities, one being the Axion sensitive cavity and one an ancillary cavity that we call a readout cavity, and they're directly coupled. They're just really going to exchange energy through some transmission line, no ferrite circulators in between, no loss associated with reflections. And the game we'd like to play is to engineer a very special interaction between those two cavities, one that corresponds to their X quadrature as being coupled, such that you can just examine this interaction Hamiltonian and see that the X quadrature of the Axion cavity is a constant of the motion. It commutes with the Hamiltonian. By monitoring the Y quadrature of the readout cavity, we can learn an amplified version of the X quadrature of the thing we care about. The back action associated with that measurement is going to be deposited into the unmonitored quadrature of the Axion cavity. How do you imagine doing that? Well, take the two cavities, join them by a transmission line, and then create some element in the transmission line that couples the two cavities such that you can vary the coupling, such the coupling can be turned on and off. And in particular, it can be turned on and off at the difference frequency and at the between the two cavities and at the sum of their two frequencies. If you do both of those things and you do them with the same strength, you create an interaction which is exactly this single quadrature amplification. It's exactly this QND Hamiltonian we'd like to generate. And the thing that, the thing that prevents you from doing arbitrarily well, or the first thing that we think would prevent you from doing arbitrarily well, is the fact that these cavities need to be separated by something like 50 centimeters for the simple reason that one of them has to sit in a great big magnetic field and the other has superconducting circuitry inside of it. Nevertheless, the standing waves that build up in there, they're going to limit your speed up of beyond the quantum limit, beyond this coherent state limit, by about 15 times. And my student came up with a clever acronym for this thing. She calls it the cavity entanglement and swapping experiment for improving readout efficiency, or ceasefire. If you want to know what the little magical thing that would do that sort of variable coupling is, it's at the moment, we think it's basically a arrangement of superconducting flux tunable inductors, similar to our parametric amplifiers, but now arranged in this bridge geometry, such that if you imbalance the bridge, that is, change the values of the inductance such that pairwise these are bigger and these are smaller, or vice versa, you create a coupling between a port, which is defined by the north-south node of this bridge, between the east-west node of the bridge. You can see that if the bridge is balanced, those are completely decoupled, and if you break that balance in the bridge, then you turn on that coupling. You can turn that on and off dynamically. All right, that's sort of what I'd hoped to tell you about today. Shown you that superconducting quantum technology, it accelerates the search for dark matter, that quantum squeezing doubles the search rate in the haystack apparatus, and we think really substantially greater speed ups are possible with some technical improvements. Well, thanks very much.
Thank you very much for this nice talk. It was quite fascinating. Are there questions or comments? Yeah. Professor Budka, please.
Yeah, thanks, Konrad. Very, very, very interesting. I have actually several questions. So one question I have is this. So some people who demonstrate various improvements due to squeezing entanglement and whatnot do not start with an experiment that is optimized. basically that's operate at the standard quantum limit. Is Haystack without squeezing tricks operating already at the quantum limits or not?
I think that's a fair question, and so I would say squeezing speeds up the Haystack search unambiguously, in the sense that there's nothing that we would have done in the experiment to include the squeezing that penalized us in some way over what we would have otherwise done. And a little bit about the beginning of the talk was trying to make that point that it's easy to circumvent or beat a quantum limit. Maybe I don't say easy. It is relatively routine in like the leading labs of the world today to beat things like quantum limits in an experiment which doesn't have some other kind of signal inside of it that you're trying to optimize. There's no question. We turn on the squeezing in the Haystack apparatus, things get better, and they get better below the state they would have been without it. However, your question, like, are we really at the quantum limit? I would say that we're a little bit, in some sense, if you use this quantum limited strategy, you can't do it perfectly. And we're a little bit imperfect, particularly in the sense that the Haystack apparatus is actually slightly at an elevated temperature. It's inside of a dilution refrigerator. It's at some ultra low temperature, but the cavity itself was kind of warm enough that it's a reasonable fraction of a thermal photon is inside of that cavity. One of the nice things about squeezing, unlike things like photon counting, which is an alternative concept for our apparatus, is that squeezing squeezes thermal noise just as well as it squeezes vacuum. So you get the benefit, you're getting the benefit above a slightly elevated background. So I think that's about as honest and complete an answer as I can give you.
But how far? So suppose you don't know about squeezing. So how far can you continue the optimization? How far are you from the SQL?
So basically, I think this, if, let's say it this way, we could choose to not use squeezing, but get rid of this last little bit of thermal excitation. I think that would also approximately double the scan rate.
Thanks so much.
Anna. You are muted, Anna.
Yeah, sorry. I said, super nice talk. Thanks a lot. It's actually very interesting to me. Also, I didn't really expect an Axion talk, but we are thinking about Axions a lot here in Mainz too. And you had really nice on-chip pictures of your structures. They look amazing. So I have a question. I have a few questions, but maybe the main one first. Doesn't your improvement with squeezing depend on the fact that you know the phase of the axion, so that it is in the X quadrature?
Excellent question. It does not. And it is absolutely correct to say that we are only sensing one quadrature. Now, you can compare, let's see if I can do this efficiently. I'll go all the way back to the beginning here. So it is correct to say that, notice that I defined this kind of quantum limit as this particular choice of state you prepared in and thing you measured. You could have made a different choice. You could have prepared in the ground state and measured both quantities noiselessly. If what you're trying to do is determine whether there is an axion signal like a kind of classical displacement like this, whose phase you do not know, it turns out that those two strategies are equivalent. You will spend the same amount of time to reach a particular precision, assuming that these two components of the axion signal are drawn from the same random distribution. And as a consequence, you can measure the X quadrature noiselessly, you can measure X and Y with added noise, and there is no benefit or cost in principle to either choice. It's a wash. At that point, when you squeeze, the fact that you get in this strategy, you give up any knowledge of the Y quadrature. You just assume that it is drawn from the same random distribution that would tell you about the displacement in the X quadrature. So clearly, once you've done that, if you improve your ability to estimate the X quadrature, you have won. You have done better. And so it does not in any sense depend on the fact if you have an unknown phase. Yes, half of the power associated with this displacement will always be in your unmeasured quadrature, but you absolutely have done better than the quantum limited strategy.
But you could have like all the power. I mean, like the axion is basically the displacement here, right? So the displacement could be along Y direction. That's
correct. The displacement could be along the Y direction, in which case you would miss it, and that seems terrible. But I think this is a little bit the unconvincing answer to Bill's question. If you asked, how long would I expect, what is the characteristic time I would expect that phase to change? In my laboratory, my terrestrial laboratory, swimming through the dark matter field, what is the correlation time over which that phase will stay the same? That's really what sort of sets this line with. And that time is just much, much, much faster. The kind of like time over which you would sample these different phases is much faster than the time you wait when you integrate. So you're really sampling over any experimentally relevant time. You're sampling many values of this phase. And so half of the power on average, half of the power associated with the displacement on average is going to be in the X quadrature.
Okay, so your mechanism survives averaging, basically. So
this is in some sense why things are so terrible, because you're power averaging, right? You're really looking at variance, and you're looking for the variance to get better, which is why you have to wait for 10 to the 6 realizations of a random process, because your variance is only a part per million bigger than vacuum fluctuations for a kind of characteristic axion signal.
Thanks.
Ferdinand?
Yeah, thank you very much for the talk. And I'm very impressed about the very low levels that you can detect. So my question is, if I would be as an atomic physics guy, I would think, okay, in this frequency range, the Rydberg atoms are certainly the best to detect any frequency. They have a huge dipole moment and they could absorb, and then one would see that some states just don't survive. Is that completely kind of orders of magnitude worse, or how does it compare?
What is the basic?
A Rydberg sensor, if you have a gas of cold Rydberg atoms and compare it to this, of course you have a tunability that is not the case in some Rydberg states, but.
Okay, so let me answer the question two ways. One is to say that Rydberg atoms were and are being pursued as a way to search for axions. There was an experiment. Okay. I think it had a name called Karak, and I don't remember what it stood for. As far as I know, I think
I put the link in the chat.
Oh, put the link in the chat. Very good.
Sorry for my ignorance.
Okay. No problem. As far as I know, I think that experiment is no longer active. I think they kind of ran out of steam for the reasons that you might guess. We are trying to join a Rydberg atom experiment to a dilution refrigerator with a great big magnetic field. That said, look, so there is another effort in my colleague Reina Murayama's lab to do exactly this, basically to do Rydberg atom things. When you're choosing between photon counting, let's just think of Rydberg atoms very generally as a kind of photon counting strategy. And there might be various ways that you count photons. You might use superconducting qubits to do it. You might use Rydberg atoms, whatever it is. The measurement operator in our quantum metrology strategy is we're going to project that harmonic oscillator into its number basis. We're going to count how many photons are in there. Or we're going to count whether it's 0 or not 0, under the assumption that it's almost always 0 and occasionally 1. Mm-hmm. That strategy will win over any of these kind of, over like a coherent state receiver in the following case. You have a number of little independent frequency bands across the Axion cavity. They're sort of these little Axion line widths. You need your dark count rate plus thermal background photon number to be less than the number of little independent frequency bands. That's essentially how you would choose between operating at the quantum limit and being able to measure 100 possible Axion lines simultaneously versus just looking over the whole frequency range, or maybe tuning a narrowband photon counter across the cavity. In our experiment at the moment, for exactly the thing that Dima hit on when he asked me, are we really at the quantum limit? In our case, we have a thermal background which is big enough that we would absolutely lose if we counted photons. But that's not a theorem that says you could never do better. And more to the point, as you go up in frequency, where the thermal distribution presumably gets smaller for the same temperature, you will eventually kind of win by photon counting. At the moment, if it were my job to photon count below 20 gigahertz, I would use superconducting qubits to do it, not Rydberg atoms. I'm not an atomic physicist. I know what I like and I like what I know. But if you have to go up higher to like 40 and 50 gigahertz, maybe the Rydberg atoms might really be the right way to do that.
Thank you very much.
Thank you. Are there further questions or
comments? I have one.
Yeah, please.
Konrad, you mentioned a couple of times the idea of this 50 ohm resistor bringing in the vacuum. So I'm taking it. I mean, if you think of this from a quantum optics point of view, I mean, of course, it is quantum optics. It's just at the microwave, and this is like having an open port on a beam splitter, where the vacuum comes in. But you mentioned a number of times Johnson-Nyquist noise, like it's thermal. Now, is this just saying, well, in addition to vacuum, you've got the black body radiation? Is this just the equivalent of that, or is there something more?
No, it's that in one dimension, right? It's if I think of my coaxial cable as a thing that supports electromagnetic modes, which have the wonderful property of being scalar one-dimensional things that run back and forth. The fact that the waves we run in one direction and don't come back mean that I am sending them to some environment, and if that environment is some temperature, then they emit black body photons.
Right.
And when I talk about it as Johnson-Nyquist noise, in my mind, Johnson-Nyquist noise kind of is Bose occupancy of the modes plus a half.
Okay. So you're lumping everything together in the vacuum and the thermal.
That's correct. That's
okay.
Right.
So one unrelated question to that. So what? I mean, of course, we have no idea what the dark matter is. So what if it's not axions? Is your experiment still sensitive to other kinds of things?
So it is inevitably sensitive to other kinds of things, and that's why we spend some amount of time worrying about radio stations and things like that.
Well, I mean, other kinds of dark matter is what I'm wondering.
So there's a related class of hypothesis known as hidden or dark photon models. The point being that in those models, you have just a term that gets added to Maxwell's equations, and those terms they don't interact with ordinary matter, though. They don't they are not shielded by the metal of the cavity. And the big magnetic field makes no difference there. In the magnetic field or not in the magnetic field, you would be sensitive to such things. In the world of these kind of hidden photons, you would still really only have substantial experimental reach here if you assume that that's like the hidden photons are really what's making up dark matter. If there's not some process we're not trying to generate them in another lab and send them through the wall into our cryostat, which is a thing that you can do, but rather we're just looking for the presence of anything that would generate an oscillatory tone with some characteristic line width in the lab, and that could be these hidden or dark photon models, so long as you assume that they're also dark matter. That would be the source. The source would be the fact that there's just a whole lot of that stuff that we're swimming through. Are there other things to which we would be sensitive that I know of that isn't some piece of junk, right? It isn't the fact that we live in an electromagnetically noisy world. Generated within the cavity, I don't know other words that I would say at this point. Like, not to my knowledge.
So does it have to be a boson field?
Does it have to be a boson?
I mean, most fundamental particles are fermions.
That's true. I mean, does it have to be a boson? I don't think there's any deeply fundamental reason why, if your mysterious fermion created some kind of electromagnetic signal inside of a cryostat, that we wouldn't see it. But in some sense, it's hard to do hypothesis testing if you don't have a well-specified hypothesis.
May I add to this, Konrad?
Please,
Diva.
I think, in fact, there is a very bizarre reason for these things to be bosons. And this has to do with what Konrad mentioned, that the dark matter has to be bound to galaxy. So now suppose it's a Fermi gas, then you can calculate the Fermi velocity, and this thing better be less than the escape velocity from the galaxy. And so from this, you conclude that if you are lighter than, say, if this particle is dark matter, and this is like a single particle dark matter, and the particle is lighter than 10 electron volt, then sorry, it has to be a boson. So this really blows my mind, that just from the fact that the darn thing is gravitationally bound to the galaxy, you can say something about its spin.
That's I mean, that's indeed the argument, but presumably, imagine there's some, I don't know, if it were a Fermi field, right? Then it certainly couldn't be that dark matter if its rest mass was basically it's associated with the frequencies we're looking at. That's or you would have to maybe it would have to be a family of fermions with some hidden quantum number that has 100 values or something. That kind of argument. But as far as what else could be making an electromagnetic signal in our cavities that it would have a fundamental origin? I think the world of theory it's a wonderful playground from which there are very few real constraints. So probably someone could cook something up. I worry that I'm missing the point of your question, though, Bill. Do you have something more specific in mind?
No, I was just when you said, well, this is a Bose field, I'm thinking, well, gee, most particles are fermions. But what Dima said answered that part of the question for me. And unless this thing is massive, so for example, I assume that WIMP searches are not assuming anything about them being bosons. They could just as easily be fermions.
Exactly. I mean, the kind of classic WIMP thing is a 10 GeV particle. It's sort of something like that. And that object is at the same, distribution, at the same velocity distribution, and at the same mass density. The number density is such that that thing is a very, very dilute gas. And in principle, it need have no particular spin. But I think this is not quite true in the sense that I think some of the WIMP searches look for particular signatures of the fact that you would scatter as a you could imagine that you could have coherent scattering that cared about the spin.
No, but anyway, that answers my question. Thanks. That's great.
Maybe Bill, to come back to your your original pressuring me on this Maxwellian distribution. I mean, one way to think about this, right, is I think if I were to imagine that the phase fluctuated more rapidly or had spatial structure on finer scales, that would be associated with velocity. Putting that gradient in the phase of the field is associated with velocity.
I suppose so. So if this was a quasi-condensate, for example, instead of a condensate.
Well, I mean,
which it will be.
Like in any finite volume, I can imagine that some number of particles are really in the true quantum ground state. That's obviously something that doesn't survive out into the thermodynamic limit. But if you were to say my phase is varying so rapidly that the line width would be broader than this number I'm giving, then that would be associated with a velocity distribution, which would be inconsistent with the Maxwellian distribution. And it would be I guess I'll say it that way.
But here maybe just again on this topic, do you expect it to be actually a narrower peak than what we are always expecting, or do you because it is a Bose-Einstein condensate, or do you expect it to be a broad? I mean, do you expect it to be narrower?
Well, I think the question in a way is if I had perfect knowledge, of the phase of the this Bose-Einstein condensate and it's my velocity through that particular patch of dark matter, then it would be spectrally narrower for sure. Right? If I could somehow lock the clock in my lab to what is a well-defined phase that sort of drifts around, then it would be a delta function in my world. So in a way, if you're asking, how do I break up the world of frequency domain when I don't when my clock isn't locked to this dark matter signal, then I have some expectation for the correlation time of that phase, and that sets a kind of natural band.
Oh, Dima, as well. I'm sure there are more questions, but we're also taking quite some time out of everyone's day, including your morning. You probably didn't even have breakfast yet.
I had a cup of coffee before I spoke, so.
That's very good. Maybe before we have last questions and Mustafa closes the seminar, I would like to advertise next week's seminar. It's going to be given by my diploma supervisor, Professor Andreas Hemmerich from Hamburg, on dissipative time crystals in an atom cavity system. And they do really have an exciting cavity atom system there, 5 centimeter cavity, 500,000 finesse, and a Bose-Einstein condensate in it. So that's next week.
Okay, now the last question. Ima.
I'm sure we can ask questions of Konrad till our night and into the morning. So, but anyway, I'm just my question is so Casper experiment, for example, is an NMR experiment, and there we have a magnetic signal, and we detected either inductively or with the squid, and I just wanted to ask you if you have some advice for acceleration for us.
I'm the wrong kind of physicist to say something especially smart about nuclear spins. But as far as I can tell, like, in the end, there is no reason, at least as a matter of principle, why if I'm looking at an ensemble of spins, as is well known in atomic physics, I couldn't have a squeeze state in that world. Spin squeezing is definitely a thing that's done routinely, as you well know. And I think there are ways to do that in the nuclear physics world, using these kind of terms in the nuclear Hamiltonian that would have like an SZ squared component that would sort of give you, I guess, what's called single axis twisting, and that prepares squeeze states. So I think the win, if you can do it, is that the time it takes you to prepare that squeeze state and the precision with which you can then measure the Larmor precession of your spins, that win in bandwidth is something that allows you to scan through frequency range faster. So I think it's I don't know a fundamental reason why there shouldn't be a kind of quantum enhancement possible in a nuclear physics experiment. What I don't know is how close you are to kind of being limited by the quantum projection noise of those nuclear spins. I think if I think about going for an MRI on my knee or something like that, I think that's rather far from that limit. But if I think of a version of Casper in gas phase, where maybe I can really be in a quantum projection limit, then I could imagine benefiting from it.
Yeah, so I think maybe we're a little far or a lot far, but hopefully we'll get close to spin projection noise. But I think Z-square interactions are indeed possible in the system that we use in Mainz, which is a spin polarized liquid xenon 129, where there are nonlinear interactions that are known. Usually they lead to some bad things, but maybe they can be taught to do squeezing instead of bad things. Yeah.
Yes. I mean, I think you know this story pretty well now, which is that, of course, you can get to the quantum projection limit in many experiments by, in the spin world, having many fewer spins. And that's rarely a win, right? That's not the strategy you want to pursue, because essentially what you would win in quantum benefit, you more than lose in reduction of signal.
Yeah.
Okay, I think we are coming to the end of our quantum seminar. We thank again the speaker, Professor Lehnert, for this excellent talk, and also for the lovely discussion that we had today. Yeah, thank you very much.
Oh, hey, thanks a lot. I really enjoyed it.
Okay.
And so it's so fantastic to see Professor Phillips coming back to our seminar. This is wonderful.
Yes. So now I officially can close the session. Thank you very much.
Bye-bye.
Bye-bye.
Bye.
Bye. Thanks a lot.